Hey guys, I tried building a 3D printed foldable long-range drone, and wow, everything went wrong. Will it even fly? Let's find out. At the very beginning, I just had this idea. I'd watched a few videos on long-range drones running on 18650 cells, and honestly, Dave CFPV was a huge inspiration. I've linked his video down in the description. And then I thought, I want that too, but I didn't just want to copy it. I wanted to add something unique. That's how I came up with the idea of making the drone foldable. And once the first sketches were done in Fusion, the idea really started to take shape. For the parts, I tried to go with the cheapest setup I could find. That's why I ended up reusing some parts from my old Cetus X. The motors were perfect for a 3-inch long-range drone. For the flight stack, I went with the cheapest all-in-one module I could find on AliExpress. For the battery, I'm using the Sony 18650 VTC6, which has a capacity of 3000 mAh and can discharge at 30 amps. The battery holder, recycled from an old battery compartment. The arms are made from 3mm thick carbon rods. I'm also using an external SpeedyBee TX 800 VTX. I had lying around. I'm a big fan of using an external VTX anyway. And for props, I grabbed a few 3-inch ones with different pitches to test out. But honestly, so much went wrong during the build that at some point I thought, it can't possibly get any worse. But of course, it just kept getting worse, over and over. 5 packages just got lost along the way, setting this whole project back by 2 months. And then there was the 3D printing. Anyone who's done it knows the struggle. The holes never fit exactly right. So I spent ages in Fusion, tweaking the designs just so making sure the carbon rods would sit perfectly, after a quick pass with a 3mm drill. This whole process took forever with so many rounds of designing, printing, and failing, before it finally worked. I printed the test parts in yellow at first, but for the final long-range drone, I wanted a cool look. Black and copper was the plan. Only problem? The copper parts turned out brittle and kept breaking. The copper PLA was just old and probably had moisture issues. After countless redesigns and drying the PLA, I finally got it to the point where nothing broke anymore. After printing so many versions, I thought I was finally ready for the final print. This was it. I'd print it one last time, assemble everything and be done. But during assembly, I realized I'd forgotten something. And it was so obvious. So, I went back into Fusion to design the right cutout, but instead of reprinting the whole piece over and over, I just printed the small section I needed to test the fit. That little shortcut saved me tons of time. With that problem out of the way, I got to work on the arms. First, I glued the 3D parts to the carbon rods with superglue. Then, I screwed the motors onto the arms. Slowly, it felt like the drone was finally coming together, and for a moment, everything was finally going right. It felt like all the hard work was paying off. Each part clicked into place, and I could actually feel the excitement building up. Putting the drone together was surprisingly fun. I was seeing the whole project take shape piece by piece. It was like the moment when everything falls into place. But of course, that didn't last long. I quickly realized that those damn parts were still breaking. No matter what I did, they just wouldn't hold up. So, I dove back into Fusion one last time, determined to fix it once and for all. I redesigned the arms, made them stronger, and made sure they'd be solid enough to handle everything. After all those setbacks, I finally had the arms just right. And when they didn't break, I knew it was the final version. The final version is now much thicker, and in the meantime, I also spent some time figuring out the best slicer settings for maximum stability. Unfortunately, I couldn't print the holders at a 45-degree angle, which would have been ideal for added strength. By the way, CNC The Kitchen has a really interesting video on this topic. It's packed with helpful tips on how to improve the stability of your 3D prints. If you're interested, definitely check it out. I'll link it in the description below. In between, I finally had a small success. I was able to configure the flight controller and VTX right away. But then I realized that I didn't have any free UART ports left for the GPS module I had planned to use. But hey, the GPS module got lost in shipping anyway, so let's just forget about that. And by the way, for the bottom plate, I used threaded inserts, which I installed with a soldering iron. I always heat the soldering iron just up to the printing temperature of the material, not any hotter. Then, just as I was about to put everything together, I realized I didn't have the right motor cables to extend the wiring. So, once again, I had to wait another 2 weeks before I could make any more progress. Once the right cables finally arrived, I could get started with the final assembly for version 1. I first placed the flight controller in position and arranged the arms to measure the exact length needed for the motor cable extensions. Then, I carefully soldered each extended motor wire to the FC. I have to admit, soldering such tiny cables onto a small flight controller was definitely a new challenge. It takes some real precision. But luckily, that part went smoothly. Little wins like this are so important. They keep you motivated in a project that sometimes feels never-ending. The power cables to the battery holder were easier. With some flux and a steady hand, I soldered them on without much trouble. I then glued the contact points in place with super glue, clamped everything down with the battery, and let it dry. This worked perfectly, and for a moment, I felt like the project was really coming together. But of course, that feeling wasn't going to last for long. But first, the project had to move forward, completely unaware of the challenges that were coming my way. In the final step, I soldered the battery holder with the top plate directly onto the flight controller. I'm a bit unhappy with this part of my design. The top plate is now glued to the battery terminals, and the wires are soldered directly to the flight controller, so I can't easily take it apart anymore. I'd really like to figure out a different approach, but I haven't come up with a solution yet. If you have any ideas, drop them in the comments. Alright, let's do the first test with the battery. This time, no smoke stopper because I just couldn't be bothered to make an adapter. It'll be fine, right? No risk, no fun. And that's when I realized there was no way the heatsink was going to fit in the bottom plate along with the VTX. But you know what? No big deal. I decided to leave it out. If I'm only flying at 25 milliwatts for now, it should be fine without the extra cooling. Sometimes, you just have to make a few sacrifices to keep the build moving. Alright, just a few more screws to tighten and this thing is really starting to come together. Looking pretty good, I'd say. Okay, now to mount and wire up the camera. And with that, she's finally ready for her first test flight. Before this thing could even think about taking off, there was still a lot of configuration to do. First up, I flashed all the ESCs with BlueJ, and believe me, this wasn't the last time I'd be messing with BlueJ. I've never had to dive this deep into different BlueJ versions and settings like I did with this project. I warned you this build was a serious test of my patience and time. Then, of course, I had to set up some basics in Betaflight, configuring the modes, like which channel arms the drone and so on. I also dialed down the rates, since I wasn't planning on doing any freestyle with this one. I made sure the motor mapping and rotation direction were spot on, and set some critical OSD parameters like the timer and voltage. Those are going to be key. And finally, I had to flash the built-in ELRS receiver. That part actually took the longest, mostly because the FC manufacturer didn't specify what chip was in there, so I had to do a bit of trial and error. But in the end, it worked pretty smoothly. But I mean, what could still go wrong at this point? It was practically ready to fly, or so I thought in my overly optimistic mind. What followed was an absolute odyssey of frustration, trying to figure out why this thing just didn't want to fly properly. But one step at a time. After the first test flights, I noticed a pretty dumb mistake. The drone kept landing right on the camera's circuit board. And yeah, I don't think the camera appreciated that too much. I hadn't wanted to make the drone taller than necessary because that adds extra weight. But I really had no choice here. Did I mention that superglue bonded my carbon rods way too well to the 3D parts? If I haven't, well, here's the proof. I had to painstakingly break the 3D parts into tiny pieces just to get the rods out. It was incredibly frustrating. To make things even more frustrating, the new part ended up heavier, despite my attempts to cut down on material wherever I could. And all of this, just because the camera needed to sit 2.5 millimeters higher. But hey, there was one good thing that came out of all this. I can now reassemble this thing in my sleep. In the meantime, I realized that my regular charger just didn't want to charge 18650 cells for some reason. So, I ended up building a USB charger from spare parts I had lying around. And here it is, the first really solid indoor test flight. Looks pretty good, right? But why is the drone wobbling like that? Must be due to the lack of PID tuning, right? Spoiler alert, nope, PID tuning had nothing to do with it. I was about to find that out the hard way. The issue was that the drone became hard to control once the battery wasn't fully charged anymore. Makes sense since lower voltage means less power. But why was this a problem for me? The drone wasn't too heavy, and the motors were standard for this kind of setup. So, I swapped out the props. The flight felt way smoother, but again, I hit the same wall. Suddenly, the drone just couldn't go on, even though the battery still had around 50% capacity left. To get to the bottom of the issue, I tried narrowing down the problem step by step. As I mentioned, it wasn't related to PID tuning. So I set up a test stand, controlling the motors through Betaflight to bypass all filters and PID controllers. Hear that? That sound is the motors straining when too much current is being drawn. I went through different possibilities. At first, I suspected the missing capacitor might be the culprit, then maybe the wires were too thin. In between, I tried every BlueJay version with various configuration parameters. I even swapped in a different flight controller from my old DrashArc. But nothing seemed to solve the issue, until it finally clicked. Listen closely. The sound disappeared when I pressed the battery contacts together. My DIY battery holder was, unfortunately, junk. The voltage drop was just too high. To fix this quickly and avoid delaying this video any longer, I went back to my original idea, using magnets for the battery contacts. They can even be soldered if you heat them only very briefly, otherwise they lose their magnetism. After identifying the problem, I decided to give the red props one more try. These props were a lot quieter and ran at lower RPMs, and lower RPMs mean longer flight times. The drone actually flew much better with these props, but I noticed it wobbled a lot more with them. So for the final outdoor test, I decided to switch back to the blue props for better stability. Alright, so the first outdoor test flight actually went surprisingly well, considering all the low points this project had. The outside temperature was around 10 degrees Celsius. Not exactly warm, but not terrible either. And let me tell you, I was about to realize just how long this thing could fly when you just cruise around with it. I didn't plan on doing any sort of long-range test, but I was just so fascinated by how long it kept going. I ended up pushing it almost to the limit, just to see how far it could really go. The drone's flight was surprisingly smooth, though I should say there wasn't much wind, and I kept my stick movements pretty gentle. I was a bit wary of whether the battery would deliver enough amps, so I mostly stuck to flying in circles. The VTX is currently set to 25 milliwatts, and it's running without a heatsink. I'm still deciding whether I even need to turn it up, or if it's worth trying a higher power setting without the heatsink. I'd bet I could push it up to 200 milliwatts if needed. I mean, most AIO FCs also don't have heat sinks, and they seem to handle the heat fine in flight. Speaking of heat, one thing I did notice was the rising temperature of the FC when I was hovering in place. I wasn't totally sure what temp limit it could handle, but I remembered something about 70 degrees Celsius. That's why I ended up flying in more circles toward the end, just to keep things cool. If summer comes around and we're hitting outdoor temps of 30 degrees Celsius, this could definitely be a problem. I might need to redesign the frame to allow a bit more airflow over the FC. But that's a challenge for future versions. As you can see, the flight controller temperature drops significantly as soon as I start flying more circles, sometimes by as much as 15 degrees Celsius. By the way, the amp readings aren't accurate yet. I haven't calibrated the values in beta flight. At the end of the flight, I realized it was showing about 50% too high. So, you can assume the FC is pulling around 7 to 8 amps while hovering. Not perfect, but definitely manageable. Alright, let's see how long this thing can actually stay in the air. I don't think I've ever been this nervous. On one hand, I was super excited to figure out the flight time. On the other, I was trying to keep stick movements to an absolute minimum to avoid any crashes. I had no idea how much the setup could handle, and then this happened. But nothing happened. No real crash, luckily. Still, for a proper long-range test, I'll have to make sure I stay in the air for as long as possible without pushing the limits too much. At some point, I started noticing the battery getting weaker. The flight controller kept trying to pull more amps to maintain power, and the quad began to wobble more and more. That's when I decided to fly lower, closer to the ground. I figured it wouldn't survive a crash from 1 or 2 meters onto gravel. Better safe than sorry, right? It was getting harder and harder not to give too much throttle. The quad was struggling to stay stable, and then it happened. One of the ESCs cut out for a moment. That was my signal to wrap up the test. Better to quit while I was ahead. By the way, stick around until the end of the video, where I'll show you a shopping cart with low-budget parts for this build. Perfect if you're looking to recreate this on a tight budget. This project kept surprising me with all the little details I hadn't anticipated. But seeing the drone finally fly was an incredible feeling of accomplishment. Sharing this journey with you all was important to me, because so many of these DIY projects thrive on tips and insights from the community. I decided to break this video into several parts. In the next part, I'll show you the first official release with a proper battery holder, which I already picked up. I'll also share all the STL files, so drop a comment on where you think I should upload them. I'm planning a proper long-range test in the next video too, with a fully charged battery that I'll drain down to about 3 volts. The only challenge might be the temperatures, which aren't ideal for a long-range test right now. Oh, and please hit that like button, it's free, only takes a second, and helps me out so much. Let me know in the comments if you'd like to see the full 18-minute outdoor test flight as a separate video. I've put together a shopping cart for you with comparable parts for this build. With the right coupons, you can get it down to around 96 euros, or about $99. Thanks for watching, and I'll see you in the next video.